There we go. Okay, this is the lesson for my applied math students. This is chapter 5, lesson 3 on standard deviation. And you know what? Actually, before we start this lesson, let's make sure we remember why we need standard deviation. I mentioned it way back in lesson 1. Remember this example here? I'm just going to go back to my lesson 1. You can flip through your notes if you like. I'm going to go back to here. Do you remember this one about the 2 batteries? This here. What do we do statistics for? Well, we want to learn about the world around us. And in this case, we want to learn, well, we have 2 batteries, which one's the better buy? Which one's going to last longer? Which one's the one to invest my hard-earned money into? Well, mean, median, and mode didn't really help very much because mean, median, and mode, as you can see, were all pretty close to each other in terms of the numbers, right? 5.7, 5.76. 5.75, 5.8, 5.7, 5.9. There has to be another way besides measuring the middle of the data to compare data sets. And there is. We can compare how much they're spread out, their measure of dispersion. We know one measure of dispersion so far. We know range. And according to the range, Y is definitely a more consistent battery. Its range is much smaller. But we could use something better than range. What we're going to use is we're going to use standard deviation. And the definition for standard deviation is, and let me get my pen back onto pen and off of highlighter. The definition for standard deviation, first of all, its symbol is lowercase sigma. It's like an O with a little hat on it or a little tail on it at the top. Some people write it with a little more of a swoop than me. So they actually see some space up there. I don't really care which way you write it, as long as it looks like a little lowercase O with a hat on it, or a little tail on it at the top. And standard deviation's definition is, it's a measure of how dispersed, which again means spread out. Here's another synonym for dispersed. Dispersed, or how varied, how much variation there is in my data. So it's a measure of how dispersed or varied a set of data is, but how spread out compared to what? Well, compared to itself in relation to its mean. No, it's the same word. The question was, can you pronounce a data or a data? It's the same word. I like data. A low standard deviation, I'll use the symbol, save some words. A low standard deviation indicates, tells us, that's the same thing, that most data values are close to the mean. A high standard deviation is more, I'll use the word spread out. Data. So in the case of that battery one, we would have found that the standard deviation for the second one was a lot smaller than the first because the numbers were clumped closer together. So the higher your standard deviation, the more spread out your data is. The lower your standard deviation, the more clumped your data is close to the mean. The formula for standard deviation is weird to look at. Is that good? No, I need to go back a little? Okay. Is that good? Okay. Well, it depends on, maybe you want your data to be spread out, right? Maybe there's something wrong if you don't get a nice wide array of data. So the question was, don't you always want your standard deviation to be low? Usually, yes, but not necessarily always. Maybe you have some sort of measurement where you're failing in the way you're producing something if you don't have a nice kind of random assortment of different numbers. And then you take the data, you take the standard deviation, and oh crap, the standard deviation's too low. All my numbers have all clumped together. Something's wrong with the process. So it depends on the situation. I would agree with you that in most cases, yes. Certainly in the case of the battery, right? It would be very frustrating if I spent 30 bucks on a battery, you spent 30 bucks, we bought the same battery, but mine lasted 5 times longer than yours. Something's wrong there, right? And certainly the standard deviation for that battery would be very high because there's a wide number of data points that are a long way from the mean. Well, you'll see actually coming up in the examples here. Okay, so the formula is, here's the formula. The formula is this sigma number, again, that's lowercase sigma, it's a zero with a hat on it, or a lowercase o with a hat on it, is standard deviation, that's the symbol for standard deviation, is the square root of, remember this symbol? We've seen it already. Sum. The sum of all of the data points minus from their mean and squared. All divided by the number of data points. There's actually a second type of standard deviation formula where at the bottom they actually say n minus 1. But that one's for large populations of data. And this is the one mainly for samples of data. So we also sometimes call this also known as the sample standard deviation formula.
So standard deviation is the square root of the sum of the data.
Minus every single data point, minus from its mean, then squared. Add all those up. So as you can see, if you had a large set of data, this would be really tedious to do by hand. This is where the technology comes in. Having said that, just so we kind of see how it works, we will do our first example by hand. We'll make a chart. Here we go. 10 hockey fans. 10's not a very big sample of data. 10 hockey fans are surveyed to determine the number of hockey games they attended through the season. And here's the results. Okay, so first of all, you might want to do this. I didn't give you any room in the notes to do this. You might want to break this out on loose leaf or something. So let's do this on loose leaf. So let's first of all do this by hand. So example 1 we'll try doing by hand. Okay, so by hand, we need to first of all find the mean of this set of data. So what's mean again? Mean is the sum of all the data points divided by how many data points there are. So in this case, that's going to be 5 plus 6 plus 7. And then there's 8 happens twice, so I'll just say plus 16. And then 9 happens 3 times. 9, 18, 27, plus 27, plus 10 plus 11. There, that's maybe simplifying my life a little. And if you count, I think that's 10 data points, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, 10 data points. So let's find the mean, first of all. So the mean of this data is 5 plus 6 is 11. 11 plus 7 is 18. 18 plus 16 is 34. 34 plus 27 is 61. 71. 82. 82 over 10, which is 8.2. So there's my mean. My mean is 8.2. Now I have to take all 10 of my data points, subtract the mean, and then square that number. Question?
What's the line over the x represent?
That's the symbol that means mean. X is just a data point. X with a bar over it is the mean. Okay, so we're going to make a chart. So on the first column of the chart, we'll have our data points. So what are our data points again? They are 5, 6, 7. 8 happens twice. 9 happens 3 times. Then 10, then 11. So there's my data. Then we're going to take each data point and minus it from its mean. Or minus the mean from it, I should say. Minus the mean from it. Then we're going to take each of those points and square it. All right. What's 5 minus 8.2? Oh, it's going to be negative 3.2. Now, what happens when you square a negative? What happens when you times a negative by itself? Becomes positive. So I'm going to get a positive answer when I square this thing. I get 10.24. All right, what about 6? 6 minus 8.2 is negative 2.2. When I square that one, I actually know the square of 22 is 484. So it's going to be 4.84. Didn't even have to punch that one. What's 7 minus 8.2? Negative 1.2. I know this square too. Quick, what's 12 times 12? 144. So what should 1.2 times 1.2 be? 1.44. What's 8 minus 8.2? Negative 0.2. And notice these next two are the same because it's the same data point twice, right? The 8 happens twice in the data. And what's 0.2 squared? When you times 0.2 by itself, you get 0.04. There's a decimal there. And then 9 minus 8.2. Finally, the numbers here turned into the positives. And 0.8 squared, 8 times 8, 64, so 0.64. And that number happens 3 times. And then there's 10 minus 8.2 is 1.8. 18 times 18 is 324, isn't it? I think so. Oops. So 1.8 squared is 3.24. Just thought I'd double check that. Haven't squared 18 in a while. And 11 minus 8.2 is 2.8. I gotta admit, I don't think I know what 28 squared is off the top of my head, so I gotta punch that one. 2.8 squared, 7.84. So, I am supposed to now add up all those numbers. Now, before we even add them up, you know what you can kind of see already? Is that notice that the numbers that are close to the mean's 8.2. 8 is very close to the mean. 9 and 7 are pretty close to the mean. Notice how small their contributions are to the standard deviation. And look at how big the contributions to the standard deviation are when you get a few numbers away from the mean. So I just thought I'd kind of point that out before we actually did the next part of the calculation. So the next part of the calculation, we've got to add all this up. So the sum of all x minus x bars is, and okay, so I'm going to punch buttons real careful now. So 7.84 is already on my screen, plus 3.24, plus 0.64, I might as well just times that by 3 because there's 3 of them, plus 0.04 times by 2, plus 1.44, plus 4.84, plus 10.24. Somebody, I hope, punches buttons with me. Make sure I didn't punch buttons wrong. I get 29.6. Okay, so there we go, 29.6. And now, let's look back at the formula. What was the formula again? The formula was, we do that part. We just got that numerator. The sum of the squares of all of the data points minus from the mean. I just did that. Then I got to divide it by how many numbers there were in the data set, and then I got to square root that. So the formula is the square root of the sum of all x minus from the mean, or x minus the mean, squared, divided by n. So I already know that this numerator is 29.6, the denominator is 10, and 29.6 divided by 10 is 2.96. Somebody could punch this through and make sure that I didn't goof up any button punching. And then when I square root that, I get 1.72. And that's my standard deviation. So going back to the notes. Oh, am I going too fast? Sorry. Okay, we good now? So go back to the notes there and we can kind of fill that in. According to our calculations, the mean was 8.2 and the standard deviation was 1.72. Was it a 2? I've forgotten already. Yeah, thing after the 2 is a 0, so 1.72. There we go. Okay. We good? All right. So we can, of course, we've used 4 different online things. There was the calculator soup calculator, there was the frequency table calculator. Even though this isn't really a frequency table coming up, we could still use that frequency table calculator. You just don't enter any frequencies and it'll do the same thing. It'll calculate standard deviation for us. But I think let's use DESMOS for the next one. So here's the instructions for how to use DESMOS. We'll use it on the next example. We won't waste our time with that first one. Select the table feature with the plus sign, and then under the table make a column and just put all of the data in X1, or if you don't like doing it this way, you could go back and do it the way that we enter data for our histograms. You can just enter an actual set of data with commas. It doesn't matter which one you pick. Okay? And once we've got our data in, we go under our stats feature and we find standard deviation. And again, we don't want the one that says standard deviation P for population. We want the one for samples. So that's the one we're going to choose. Okay? All right. So let's do an example. The prices of 10 cars available for sale at 2 different dealerships are listed below. There's dealership A, there's dealership B, and we want the mean and standard deviation for each set. Okay, so I'll pause the video while people entered in. I kind of did this ahead of time. So I actually did it this way. I just realized I did it differently from the notes. That's actually from my last class. That's not what I wanted. Yeah, you can leave that. Hang on. Do I have it open over? Oh, I must have accidentally closed it. I thought I had it open. Oh, there it is. I did leave it open. There you are. 5.3. There we go. So I will give the class a minute here. I'll pause the video. Enter the data from dealership A and dealership B, and you can enter it either as a chart. It wouldn't matter, or you can enter it this way. Just A equals and then just list the numbers. Okay? Yes. Okay. So please enter it and away you go. And standard deviation and mean, we'll show you how to calculate in a minute. So we'll give people a minute to enter data, and we'll be right back. And we're back. Okay, so this data has been entered into DESMOS right here. And I entered it as just a list of data numbers, and I asked it for a mean, so I just typed in the word mean. Or again, you can just find mean by going to your keypad here, going to functions, and under stats, there's mean. And then I found standard deviation. Again, we don't want the population one with the P, we want this one, standard deviation. Can everybody see that? That's the one we were looking for. And for A, my mean is 25,000. For B, my mean's quite a bit higher, 47,000. But again, in a car dealership, that just means that one lot has more of the expensive cars than the other. That doesn't really explain how close their prices are in comparison to each other. So the standard deviation for A is still quite a bit higher. Even though the mean was lower, the standard deviation is quite a bit higher than it was for B. If anybody did the data the other way, is that the question I have? I'll get to your question in a sec. If anybody did the data the other way, you entered it as a chart where this was A and this was B. I think you can rename these, can't you? Can you rename these? A, yeah, you can, and rename this B. So if anybody did it like that, then again, you can just go to cell 2 here once you've got your data in and say that you want the mean. You can type in mean or you can go look for it and then open a bracket and A, and there's the same number we had in the other one. And then we want the mean for B. Oops, lost my bracket. There we go, mean for B. And again, for standard deviation, you can just type in STDEV, standard deviation, and you want A, and there's that 9,500 number, and the standard deviation, STDEV, open a bracket for data set B, and there's that 7,200 one. So let's go back to our notes and put in our data, put in what we got. So the mean and the standard deviation. So for dealership A, the mean, I'll use symbols. The mean is $25,010, and the standard deviation was $9,568.66. For B, the mean average was $47,065. So the mean price of cars is much higher in B, but interestingly enough, the standard deviation was quite a bit lower, $7,272, and around, it's money, so 25 cents. Makes sense to do that, I think. All of these are in dollars, obviously. Yeah, I think so. Let me go back to it. Some 25,010. Well, I did it on two different ones, and I got the same number both times. There it is in the first one. There it is in the second one. You must have entered a data point wrong. Okay? All right. What I haven't shown you yet is what if you're doing this on the TI calculator? Well, once again, on the TI calculator, you'd have to go to your stat list, edit, whatever data you have in there, clear, and clear, okay? And then you enter your data points. You enter them in exactly the way that you did a second ago. So 22.5 zeros, and so okay, I'll pause, and I'll continue the video after I've gone through this. And I'll enter the data, then show you what buttons to punch to get standard deviation on the calculator. So if you're using a calculator at home watching this video, oh wait, I just did that one wrong. It was 22.5, then 31.4. Okay, so if you're watching this, pause the video and keep entering the data. Put dealership A in list 1, we'll put dealership B in list 2. So I'll be right back. We're back. So I just realized that the calculator uses, for the sample standard deviation, doesn't use the sigma symbol. They use an actual, well, they do, they just use an uppercase one. So what I was showing people here, let me first of all go back to the question. there we go. So we're doing this question here. And this is my standard deviation, 9568.66. And you can find that on your calculator by going to, first of all, enter all your data. So you enter, I put dealership A in the left column, dealership B in the right column. And then I go stat, calculate. It's one variable statistics because there's only one variable here, the price of the car. And then I want this for L1, so shift L1, and then hit enter. And careful, this is not the one I want, this is the one I want. They use a capital sigma for their sample standard deviation, which is the one we want. We don't want the population one. So they want the, so on your calculator, it's the capital sigma, which looks like an S on the calculator. So yeah, not the one below it. So this is the one we want. 9568.66, which is what we had when we did it on DESMOS. And then if I do this for the B, again, stat, calc, one variable statistics, but this time I want to do list 2, because list 2 is where I put it. And then there we go again, 72.24. They rounded it, well, we rounded to 2.5, but there it is. So there we go. So there's how you find standard deviation when you're doing a sample, because notice it says the prices of 10 cars available for sale. It doesn't say it's all their cars. It doesn't say it's the entire population. It's a sample, and that's why we use the sample one. So now let's actually look at the interpretive part of it. Which dealership's prices have the greatest standard deviation? And the answer is A. And what does that mean? That means dealership B has more, let's say, consistent prices, right? They're closer together. More of dealership B's prices are closer, to its mean than dealership A. And that's basically what you can say. So that's the car dealership one. Now for example 3, they actually want us to try to do this without technology at first. They want us to kind of look at it and use our estimation skills. So let's read example 3 together. For the following frequency tables, estimate the mean and determine which has the least and greatest standard deviation. Okay, so for the following frequency tables, so let's take a look at these frequency tables. So remember what this means, right? This means that the value 25 happened 12 times. We've seen this one before. The value 26 happened 14 times. The value 27 happened 12 times. Which one do you think would have, well, let's estimate the mean. So the mean here would be 25 12s plus 14 26s plus 12 27s plus 8 28s plus 4 29s, and then divide that by however many there are here. What is that? 10, 20, 30, 32, 36, 38, 46, 50. It looks like it's 50 data points for at least this one. So if I were to do that, I actually did calculate it already. My mean here is 26.56. My mean for this one, what do you think, just looking at it? Do you expect a higher average or a lower average?
Higher.
Why do you say higher?
There are 25, 28s.
Yeah, there's way more 28s, and there's 4 30s. The other one didn't have any 30s. And it's actually not by much, but you're right. This one was 27.72. All right, look at the next one. What do you think? Estimate the mean. What do you think for this one? It's going to be pretty close. It actually ends up being between these two. Because notice this one's kind of very evenly spread out. It does have more 30s. This one didn't have any 30s. So it's going to be higher than this one. But this one here had a big glut of them around 28. This one doesn't have very many in the 28 range. So this one actually ends up being 27.5. And for this one, what are you looking at? What do you think? This is interesting data. Check this out. You have 25 at the high end and 25 at the low end. So what's the average going to be? Well, the average here is actually going to be right in the middle. This one you could probably you could get the exact answer without estimating. Can you see that the mean on this one has to be right between 27 and 28? It's 27.5, because exactly half the data is 25 and half the data is 30. Okay, now, looking at this data, which one do you think going to have the lowest and highest standard deviation? So what is standard deviation again? It's the measure of how close all of your data is to its mean. Well, which one's going to have the highest standard deviation? The mean here is right in the middle. All of the data is either way above it or way below it. So I would think the one with the greatest standard deviation should definitely be D. That one I think is obvious. But which one has the lowest standard deviation? The next question. What do you think? Why is it D? Okay, because take a look at the data. Imagine this is a graph. Imagine this is a bar graph, right? At 25, you have this great big, and at 30, you have another great big one. And where the actual mean is, you don't have any data. So this one, more of the data is farther from the standard deviation. So it's definitely going to have the biggest standard deviation. That's the worst diagram ever, but you get the idea. Okay, now what do you think? Which one is it clumped to the closest? Which one has more of its data near its mean number? And the answer is B. Can you kind of see that? Notice 25 and 10. By the time you get to the ends, you only have 2 and 4. This one has 12 at this end. This one has 9 and 8. So yep, the answer is B. And I actually did run these just to kind of make sure that I had it right. I did find the standard deviations, and I'll show you how to run this. Remember, frequency tables are not something Desmos is particularly great at. So I would do this one using the frequency table calculator. So again, go to our blog. Remember, they're all listed on the blog. Go to the frequency table calculator. And then, okay, so I'm going to enter this. So my data values are 25 to 30. So 25, 26, 27, 28, 29, 30. So there's my data. And remember, the way to do this is you actually now hit enter. And on the next row, you put frequency and a colon. And then that tells the calculator that each of these is the frequency of those data points. So first it was 12, 14, 12, 8, 4, 0. And then you go calculate, and it'll make you a frequency table, but then it'll give you your standard deviation. And this one is 1.235. So my first one was standard deviation is 1.235. Okay, now I'm going to go back and I can just do this really quickly. All I have to change for this one is the frequency numbers. So for the B one, the one that we think will have the smallest standard deviation, the frequency numbers are 2, 5, 10. So 2, 5, 10, 25, 4, and 4. 25, 4, 4. And recalculate. And this one had a standard deviation of 1.132. So let's go back and put that down. So my standard deviation for this one is 1.132. For C, the one where the data seems very evenly distributed, because, I mean, take a look at how each category has, this would be the flattest looking histogram, right? So go back to the table. Yeah, we started by estimating this.
So what was the point of estimating?
Well, we just wanted to see if we could kind of look at the data and get a sense of it. Somebody's asking, why bother estimating? Well, we just wanted to get a sense of the data before we confirmed our suspicions with the calculator. So this one's 9, 8, 8, 8, 8, 9. 9, 8, 8, 8, 8, 9. Do I have enough 8s? 1, 2, 3, 4. Do I have 4 8s? I do. Recalculate. And the standard deviation for this one is 1.746. So go back to our data, and this one is standard deviation is 1.746. And finally, the one that we thought would have the highest standard deviation. We were expecting it to be this one. So go back to my data calculator here. Yep. And it was 25 data points there, then none in that one, none in that one, none, none, right? 4 zeros in a row, 1, 2, 3, 4, and then 25. And the standard deviation for that one, recalculate, was 2.5, which is definitely the biggest standard deviation by quite a bit. So the smallest one was B, we were correct about that. The biggest one was D, we were correct about that. So there we go. So you can now try some of these for yourself. Again, the homework here, let me go back to, go back. There we go. The homework is page 233, numbers 2, 5, 7, 8, and 14. 7 and 8, I believe, are about Blue Bomber legend Milt Stegall. Very exciting. And I really like question 14. Question 14's kind of got a neat piece of data to it. And there we go. So you can have the rest of this class to work on it. Tomorrow we're going to start learning about something called the normal distribution. I also have a little video I'm going to put on the blog that explains standard deviation really well. I think it's a nice little professionally put together video. So look for that. I just have to find where I bookmarked it, and then I'll add it to the blog. So check the blog later for that video.